Hello, good morning again. Easy lecture series on modeling and simulation of earthquakes, soils, structures, and their interaction. Uh, Today with me are Dr. Han Young
Hello again.
and Mr. Heshen Wang. They're going to
Hi.
be spending some time talking about calibration of these models. We will start with Mr. Heshen Wang, who's going to talk about how to calibrate some common models, some practical models for modeling of clay. So
Okay.
Heshen, please. Oh, yes, no, I'm recording. I always forget to record. Okay, go ahead and share your screen and we can get going.
Okay. Yeah. Sure. Yeah.
Excellent.
We already talked about the elastoplastic model that we can use to modeling the behavior of the clay. So on this presentation, I'm going to talk about how do we calibrate these parameters for those elastoplastic models. And yeah, yeah. As we mentioned before, we can use the Mises elastoplastic model with Armstrong-Frederick translational kinematic hardening to modeling the behavior of the clay. And we have 7 parameters for this model. And the first parameter we can comes from the unit weight of your soil. And also we have 2 parameters for the elasticity that can be calculated from the shear wave velocity and the P wave velocity. And we also have a parameter which is the Mises radius that will control the size of the elastic region. And there's another 2 parameters, Armstrong-Frederick HA and Armstrong-Frederick CR, that will control your post-yielding hardening behavior. We're going to calibrate these 2 parameters to match the undrained shear strength of your clay. And for the isotropic hardening rate, we always set it as 0 in the modeling of the clay because we do not want to have isotropic hardening for the soil behavior. Yeah.
Just to note, so a typo on the title, that's fine. So this is elastoplastic model for clay, not for interface.
Oh, sorry.
Yeah,
Yeah.
that's fine.
Yeah.
That's
Okay.
fine. Just keep going.
Okay. Yeah, yeah. So let's say, for example, we have given the clay with the density rho is equal to 1,954 kilograms per meter cubic, and we also know the shear wave velocity and the P wave velocity of this clay, and also we are given as a clay as a undrained shear strength with 40 kilopascal. So then we can firstly calculate this to elasticity parameter, which is the elastic modulus and Poisson ratio through these conversion equations from the elasticity. And from this VP and the VS, we can calculate the elastic modulus as 203.2 megapascal and the Poisson ratio as 0.3. And also for Mises radius, because for clay, it usually plastify at a very low stress level. So we will set relative small for Mises radius. We have been using 10 kilopascal here. And initially we can choose some Armstrong-Frederick parameter for HA and the CR. Here we have been using 5 megapascal for HA and 60 for CR. And as I mentioned before, we're going to put 0 for isotropic hardening. And then we can do a simple, Gauss point shear test or the element shear test. We can get the stress strain response for these trial parameters. And as we can see here, since our target shear strength is 40 kilopascal, so we are a little bit higher with this set of parameters. So that means we might want to either increase our HA or reduce our HA or increase our CR, because remember the HA over CR will control the plateau of the shear strength. And also, we might also feel like, for this set of parameter, the soil is a little bit too hardening too fast, because from my experience, I usually check, when the shear strain is about 1%, generally, the stress level of the shear stress should be around half of your eventually your shear strength. So here you can see we are a little bit stiff, hardening too fast. So we might also want to reduce the HA a little bit, so that it can be a little bit softer. So then you can do some fine tunement for these 2 parameters. I reduce the HA a little bit, and also reduce the CR a little bit to lower down the plateau. So as you can see here, if we choose HA as a 3 megapascal and the CR as a 50, then we can hit the 40
Yeah.
kilopascal the shear strength, and also we can have relatively reasonable behavior for the clay.
Yes.
Yep.
Excellent.
Yeah, I think you can look more information for this reference.
So if you go back for a second,
And
so this is really can I
acknowledgement? Yeah.
Go back to the cyclic stress strain response. Yes. So this is really important. So
Yeah.
so you always try some initial trial, and then you do a single element, or we also have implemented the stress strain response directly, that you can test the different types of stress strain behavior directly at the constitutive level using that Bardet constraint. But you do a sensitivity study, and you see and you try to fit. You have to have some type of test data, or you have to have some information, and then you try to fit that, and then you end up with a response that looks like this. Yes, I'm sorry. Go ahead.
Yeah, if I may. So I just had one thing to add. Is so as you mentioned before, we do have that Bardet driver, and we actually have some really nicely written scripts that can easily be used to do this material level test, so that the user don't need to go back and forth to do a lot of operation. You can run simply just one command, and then when you test those parameters, and then it will automatically generate a plot, so you can directly see if you have the desired response that they're trying to calibrate for.
Yes. Yeah. Good. Excellent. Thank you very much. So go back to, I guess I cut you off at the last slide.
Yeah, I think then we're gonna give thanks to our collaborators and this funding resources, and you can check more information on our Real Easy website. Yep.
Thank you very much. So I'll stop recording.